Oh god, oh knackered. Luckily, I've smashed off a load of coffee, so hopefully I get a bit of a buzz on. And I'm going to need to, because we've got a bit of stats and mechanics to do. It's paper 3 from the sample assessment materials for Edexcel. Let's crack on. It's going to be statistics first. Let's have a bit of a look at what it says. So, the number of hours of sunshine each day, Y, for the month of July at Heathrow. I feel like it's going to be a bit of a large data set here. It just seems like that kind of question. Summarised in the table below. A histogram was drawn to represent these data. The Y is 8 to 11 group was represented by a bar of width 1.5 and height 8. Find the width and height of the 0 to 5 group. Okay, so they're not actually asking us to draw the histogram here, which is nice. Let's draw the 8 to 11 bar, just a rough kind of sketch. Might help us here. So imagine it's that, okay? We're told that the width is 1.5 and the height is 8. Okay, so I really need to sneeze. Nah, right, we're going to go on. We're going to go on. This other bar that we're interested in is going to be corresponding to the 0 to 5 group. So I can instantly kind of get some information about this width here. It finally came. There we go. Essentially, the 8 to 11... Right, we're in. I'm leaving it in. The 8 to 11 group, the class width is 3, isn't it? Because there's 3 people between 8 to 11. And that class width of 3 is represented by a width of 1.5 on the bar. So, it looks like the width of the bar in centimetres is half of whatever the class width is. So, if my class width is 5... Oh man, I can't stop. If my class width is 5, for example, 0 to 5, right? Well then, the width of it is going to be half of that, so 2.5. So I'm going to get 2.5 here. Okay, fantastic. So I know what the width of this thing is. It's going to be 2.5 centimetres. What about the height? So, with histograms, basically the area of each block is not necessarily the frequency, like the amount of people in it, but it is at least proportional to it. So, there are supposed to be 8 people in the 8 to 11 group, okay? So we can clearly see that this isn't the same as, you know, the area of this rectangle, but it's proportional. So if I was to do 1.5 times 8, that's going to get me a value that is proportional to 8. That's proportional to the frequency. So something proportional to 8 is going to be some constant of proportionality k multiplied by 8. I can work out this k and then apply it to my rectangle here, just using this exact same equation. So cancelling 8 from both sides, I get k is 1.5, okay? Now if I do this exact same equation for this, I'm going to be good, because this was width times height. Okay, so width, 2.5, times height, we don't know it, so we'll call it h, is going to equal exactly the same equation, k times by, and then the frequency, right? The amount of people in this class, which we know to be 12. So it's going to be k times 12. We know what the value of k is. It's 1.5. So this is just an equation that I can rearrange for h now. So if I divide both sides by 2.5, I'm going to get h as 1.5 times 1.2 times 12 over 2.5. This is going to get me the following: 1.5 times times 12 over 2.5. Got there in the end, and that's going to get me 7.2. So the width is going to be 2.5 centimeters, and the height is going to be 7.2 centimeters. Sick. Part B, use your calculator to estimate the mean and standard deviation of the number of hours of sunshine each day for the month of July at Heathrow. Give your answers to 3 significant figures. Okay, so we're going to use that calculator. Why does it say estimate? It says estimate because we have grouped data here. Because if we have grouped data, we don't actually know these data points. Like between 0 and 5, we don't know where they are. We don't know that there was one at 1.2, one at 4.1. All we know is there were 12 in this class. So the way we estimate it is we say, okay, let's just estimate that they're all at the midpoint. So that instead of, 12 being scattered around 0 to 5, we're just going to estimate that there's 12 at 2.5, the midpoint. There's something I want you to do first. Your calculator might already have it, but because we're working with frequency, we need to make sure that frequency is turned on. So press Shift and then Menu, so it'll be like Settle, right? And then go down and press Statistics. And then it says Frequency, question mark, on or off. Make sure it's on, so press 1. Now that we've done that, press Menu and go to 6, which is Statistics. We've got one variable here, so we're going to press 1, and then we can put our table in. Now, as I said, on the X column, we're now going to put the midpoints in. So I'm going to put 2.5. Halfway between 5 and 8 is 6.5. Halfway between 8 and 11 is 9.5. Halfway between 11 and 12 is 11.5. And halfway between 12 and 14 is 13. Now go back up and to the right and stick all the frequencies in. So it's going to be 12, 6, 8, 3, and 2. Sweet. We've got our data stored in the calculator. We're now going to press Option or OPTN. It's at the top left, just under the Shift button. Number 3 is one variable calculations. That's what we want here. And look, straight away you're getting an absolute plethora of grim-looking numbers and symbols. But we want them. So we want the mean here, which is X bar. So straight away to 3 sig fig, this is going to be what? 6.63. And then we also want the standard deviation. So we get that. That is the sigma x thing. So you'd write that like this with a subscript of x. And that to 3 sig fig is going to be 3.69. That's part B. Let's have a look at C. The mean and standard deviation for the number of hours of daily sunshine for the same month in Herne are 5.98 hours and 4.12 hours. Let's get these down. So we've got something else. Let's call it Y, for example. Probably not a good idea because Y was actually the first one, but we only live once. I can't be bothered changing it. So Y bar for this one is 5.98. And then the sigma Y, the standard deviation, is 4.12. Thomas believes that the further south you are, the more consistent should be the number of hours of daily sunshine. Okay, well, what does more consistent mean? Does it care about the means here or the standard deviations? It cares about the standard deviations. Because more consistent just means like, you know, standard deviation means I vary from the mean more. I have a higher variance. So for example, if the mean is 6.63, but the standard deviation's, you know, really high, it's like, okay, my mean's here, but loads of the time they're over here, they're all the way over here. If my mean was 6.63, but I've got a tiny standard deviation, it's like, yeah, the average is 6.63 and they're usually really close to that. So basically, if I have a lower standard deviation, I don't vary as much from the mean and I'm more consistent. So let's have a look at which one has a lower standard deviation here. We can clearly see that the standard deviation for Heathrow is less than the standard deviation for Herne, meaning that Heathrow must be more consistent, right? So Heathrow, you know, has a lower standard deviation, so it is more consistent. So that's kind of the maths they want. There's an annoying little thing here, because you might be like, well, what's more, you know, what's further down south, Heathrow or Herne? Either you're pretty good at geography, or annoyingly, you're going to need to know this from the large data set. So it turns out that Herne is further south. So basically, here we've just shown that actually Heathrow, which is further north, is more consistent. So Thomas is chatting, and he basically is chatting because Thomas thinks that the further south you go, the more consistent it is. But this suggests otherwise. So Heathrow has a lower standard deviation, so is more consistent. Herne is, you know, further south than Heathrow. You know, so the data does not, you know, support Thomas's belief, essentially. Yeah, does not support Thomas's belief. So really, you could have done all of the maths there, and then, you know, you could have forgotten about which one's further south, Herne or Heathrow, which, you know, I wouldn't blame you for doing. Guess, right? Let's say you got one of the marks from doing the standard deviation, flip a coin, and then, you know, on the second mark. So maybe, you know, you're not really, it's not catastrophic to not know the large data set at that point. Part D. Estimate the number of days in July at Heathrow where the number of hours of sunshine is more than one standard deviation above the mean. Okay, well, what is one standard deviation above the mean? Surely we should work it out, right? So essentially, that would be the x bar plus the sigma x, wouldn't it? Let's work it out. So, let's do 6.63. I need to get back to normal mode, so menu 1. 6.63, add 3.69, which is going to get me 10.3 to 3 sig fig, right? Okay, so I'm going to need to use what we call linear interpolation here. It's essentially, I've got these different classes, right? So 0, 0 to 5, 5 to 8, 8 to 11, 11 to 12, and 12 to 14. And then I've got the, the frequencies. So up until 5, there's been 12 days already. And then up until 8, there's been another 6 days, so there's been a total of 18 days. And then up until 11, there's going to be another 8 days, so that's going to be 26 days, right? But now look, 10.3. So this is the frequency on the top, and then this is the actual hours on the bottom. We're kind of interested in this 10.3 here, which is in this 8 to 11 class, aren't we? So we have this bottom number, we want the corresponding frequency, because then we can say, okay, I estimate that, this many days are to the left of it, to the right of it, etc. So it'd be good if we knew, kind of, as a proportion of the total class, like how far in we are, if that makes sense. Because obviously the total class width is 3, and then the proportion that we are, we're this far into this class, this red line. So if I could get the proportion, so for example, I'm, halfway into the class or a 10th into the class, then we can apply that proportion to these numbers and work out what this number should be. So to get this red, what am I going to do? I'd just do 10.3 minus 8, wouldn't I? That would get me the length of that red line. And then if I divide that by my class width, which is going to be the difference between 8 and 11, which is 3. So, we're basically told, we know that this whole class, so many words, man. Need this coffee to kind of sort me out. So that's, the proportion is going to be the red divided by the black, right? So 3. So let's work that out. So if I was to do 10.3 minus 8 all over 3, that's going to get me 23 over 30. So that's the proportion into this class that I am, isn't it? So here's what I need to do. If I was to now try and work out this blue line, that's going to be 23 over 30 amount of the total class width in terms of the frequency. So it's the same equations, isn't it? So it's going to be 23 over 30 multiplied by this class width. Well, this class width is going to be 26 minus 18, which is going to be 8. Okay? So this tells me how far above 18 I am. So 23 over 30, which I've got stored in my answer right now, which is nice, multiplied by 8 gives me 92 over 15. Let's keep it as a fraction for now. Okay, so that tells me that this blue line is 92 over 15 long. But remember, this is 18 here, so we'll do 18 plus that number, so 18 plus ants, and then that's going to get me 24.13 ... Cool, so that tells me that in terms of a frequency, I'm at the 24.13 day, right? But it says, so there's going to be 24.13 on this side, and then an amount on this side. We want to know how many is on this side, right? Above the mean, above one standard deviation above the mean. So there's 31 days in July. So if I was to do 31 take away answer, that's going to be it. That's going to tell me that, all over here, I get 6.86 ... days, or in other words, 7 days. Cool. Can be a bit mad linear interpolation. I didn't want to spend too long on it now. But yeah, I would definitely suggest going to learn it separately with a bit more time if that confused you. Okay, cool. So last couple of parts now. Helen models the number of hours of sunshine each day for the month of July at Heathrow by a normal distribution with a mean of 6.6 and a variance of 3.7 squared. Use Helen's model to predict the number of days in July at Heathrow when the number of hours is more than one standard deviation above the mean. Okay, well again, we're going to do, what is one standard deviation above the mean in this case? It's going to be 6.6 plus 3.7. So that's going to be 10.3. Okay, and then we say, how do we get this probability? It's going to be using the normal distribution. So if I was to go menu, and then 7 for distribution, they've even got a picture of a normal curve on it. Normal CD, I want the cumulative distribution here. And I want my lower value, I want basically everything here. I want greater than 10.3. So my lower value is going to be 10.3. My upper value is essentially infinity, right? But you just want a massive number. Just get the 9 and just go like that. Just smash the 9 button. Massive number, obviously. And then sigma, which we know to be 3.7. And mu, 6.6. Press equals, gives you your probability. So it's going to be 0.15865 ... And I think we're generally working with 3 sig fig here. So it's going to be what? 0.15923 significant figures. However, that's not actually my final answer because it says the number of days in July. So actually what I'm going to do, I'm not even going to round that, but I've still, I'm going to go back to the normal mode of my calculator. That's the proportion, isn't it? Because it's the probability. Multiply that by the number of days in July, which is 31. So if I do 31 and then times by all of this stuff, the 0.15865 ... That's going to be 31 multiplied by 0.15865. That's going to get me 4.9, which is about 5 days. Sweet. Use your model from parts D. Use the answers to parts D and E to predict. To comment, so I can't even read at the moment, on the suitability of Helen's model. Okay, well, Helen's model predicts the answer to be 5 days, but the data predicts it to be 7 days, doesn't it? So that's a bit of a difference. So I would say, look, Helen's model predicts 5 days, but data predicts 7 days. So probably, it's a bit too far, isn't it? A bit too far, doesn't seem too suitable, really, I would say. And obviously that prediction is, the amount of days of rainfall of more than one mean plus the standard deviation. Cool, I feel like I've done about half an hour on this question alone, so we'll cut it there and try and crack on with question 2. Question 2, let's do it. A meteorologist believes that there is a relationship between the daily mean wind speed, W, and the daily mean temperature, T. A random sample of 9 consecutive days is taken from past records from a town in the UK in July, and the relevant data is given in the table below. Sick. The meteorologist calculated the product moment correlation coefficient for the 9 days and obtained R as 0.609. Explain why a linear regression model based on these data is unreliable on a day when the mean temperature is 24. Because it's extrapolation, isn't it? Like, look at the temperatures, right? So what we're doing here, when, with this linear, here we go. Let's give you a bit of an example here. I'm plotting my T and my W, right? Got all these different temperatures, all these different Ws, and the relationship between them is plotted. And then we're maybe going to hopefully get some kind of, line of best fit, linear regression out of it, or relationship. Look at the different values that T goes between. It's about 13, and then the highest one, is 19.3, isn't it? So look, the highest value here is about 19.3, and the lowest around 13.2, I believe. So here's the thing: you can do all you want with these values here. You might get a really good relationship between them. It might be like all right down here, and you can say, oh, look at this line of best fit, cool, kind of thing. But you would still have absolutely no idea what's going to kick off over here when T is, T is 24s all over here. You have no idea what's going to happen. You have absolutely no reason to believe that it would just carry on like this forever. It's clearly not, is it? Because, it's not like the temperature can just go infinite, can it? So, when you are trying to make estimates based on values that are just completely outside of the data that you already have, that is called extrapolation, and it's not really good. If, however, it said, estimate what the wind speed is going to be when the temperature is 15, that kind of works, because 15, nicely in your data, you would go, okay, 15, make a line here, Pretty sweet. That's called interpolation. You're inside the data that you have, and that's generally acceptable. So basically, look, 24, 24 is outside of the range of data we already have. Range of data we already have for temperature, and therefore extrapolation. And then, yeah, that is why basically it's just going to be unreliable if we were to do that. Cool. What about part B? State what is measured by the product moment correlation coefficient. So it is basically to do with the relationship between these. So, if it's 1, it's a perfect linear relationship going positive. If it's -1, it's a perfect kind of negative relationship like that. So it basically just explores, or measures, I suppose, the linear relationship between the two variables. If it's 0, it's basically saying, look, that there isn't one. Cool. Okay. C. Stating your hypotheses clearly. Stating your hypotheses clearly test at the 5% significance level whether or not the product moment correlation coefficient for the population is greater than 0. Okay. So what I want to do is introduce you to something in your formula booklet, and that is the tables here. Because this literally tells you what to do. It is the critical values for this hypothesis test. So kind of at high level, what's going on here is that there's this population correlation coefficient, and then the null hypothesis, right, the H0 is basically, look, as it stands, there's no relationship between these things. In other words, rho is 0. There isn't some linear relationship between W and T, rho is 0. And then we're saying, no, actually, we think there is one. So my alternative hypothesis, the thing that I think is true, is actually, no, rho is greater than 0. In other words, I think that if temperature increases, wind speed will increase, for example. So the question is, and then, I then actually did, well, not me, this meteorologist, did a little sample, and he got a sample value of rho, or R, right, because it's the sample, and he got 0.609, which does suggest there is a bit of a relationship, that's quite a lot higher than 0, but is it actually statistically significant? How do we know? We use these tables. So this says these tables concern tests of the hypothesis that a population correlation coefficient of P is 0. The values in the tables are the minimum values which need to be reached by a sample correlation coefficient in order to be significant at the level shown. Meaning that, there's different values that this R can be, right? It can be anything between -1 and 1. We're trying to show that it's greater than 0. What it needs to do is it needs to hit some critical value. If my value of R is greater than that critical value, I've got enough information. I've got enough evidence. It's like, yeah, no, that's bigger than the critical value. That's high enough for me to think, you know what? I think that H1 is true. I think it's greater than 0. If it's not past the critical value, you've not got enough evidence there. So all we do in this case is we look at the significance level and sample size that we have. Our sample size is 9, and our significance level is 5%. So here's what I do. Sample size 9, I'm looking at this row here. Significance level of 5% corresponds to 0.05. So all I want to do is find this here. That's 5% significance, sample size of 9. So look, my critical value here is equal to 0.5822. But the value I got was 0.609. In other words, it's in the critical region, isn't it? It is past that critical value. So I will say that my value of R is inside the critical region. Therefore, there is enough evidence to suggest that, to reject H0 basically at the 5% level of significance. That's key to say, isn't it? Because there might not be enough evidence at the 1%, but there is at the 5% in our case, at the 5% level of significance. And let's make that a bit bigger for you. So yeah, I think that is more than enough for my hypothesis test there. Using your knowledge of the large data set, suggest giving your reason the location that gave rise to these statistics. Oh, and it says using the same 9 days, a location from the large data set. Okay, so it gave T, in other words, T bar, in other words, the mean temperature as 27.2, and this is in degrees C. And then the wind speed, the mean wind speed, as 3.5 knots. Okay, so again, it's a large data set question. It's only 1 mark because I think, you know, it would be quite tough to make students lose so many marks if they just didn't know this bit of knowledge. Essentially, you've got a few different locations with this large data set. You've got a few in the UK, but is there anything here that would probably suggest, you know, this probably isn't the UK here? Well, look, a mean temperature of 27.2. I should be so lucky, mate. 27.2 over 9 days in the UK. Mate, not a chance. Not a chance. So it's definitely not going to be anywhere there. Now, there are some hot places. There's Beijing. There's Perth in Australia. Quite hot. Jacksonville. So then, you know, just the temperature alone isn't really enough information for us to decide. However, this probably is. So this is wind speed, and this is quite low. 3.5 is quite low, okay? Perth is on the coast, right? So it's actually probably going to be quite windy. Somewhere, you know, it's quite hot, but then quite inland as well, because it might not be as windy, would be a great option here. So I think the best option in this case would be Beijing. Again, yeah. It's hard for me, if you've not seen the large data set, it's hard for I can't say anything that's going to make you understand this right now. You really just need to go and look at it. You know, there's no magic formula here. You're not going to be able to get the marks if you don't know what's in it. Simple as that. So it's going to be Beijing, you know. And if you want, you can say, you know, because the temperature is quite high and wind speed relatively low. Relatively low. I think, yeah, that'll do the job here for question 2. Question 3. A machine cuts strips of metal to length L centimeters, where L is normally distributed with a standard deviation of 0.5. Strips with length either less than 49 or greater than 50.75 cannot be used. Given that 2% of the cut lengths exceed 50.98, find the probability that a randomly chosen strip of metal can be used. Okay, so we're in the normal distribution, you know, we've got this L, it's normally distributed, but what's different here? We don't know mu, do we? So usually we know mu. We'd be like, oh, mu is 50, standard deviation's this, give me some probabilities. You use your calculator, you do all of that stuff. The problem is we've not got mu. So what we're instead gonna have to do is use some other piece of information to get mu. And that's why this question is a 5 marker. There's gonna be a bit of juice here. So we're going to need to first of all get mu, and then once we got that, then it turns into a normal question, and we can work out this probability. So we do know sigma, it is 0.5, so in the distribution that would be represented as 0.5 squared, because it's the variance. And mu is unknown, is it? Okay, the piece of information I'm going to use here is the fact that 2.5% of the cut lengths exceed 50.98. So, just kind of to represent, you know, what this actually means. I've got my mu in the middle here, which I don't know. And then 50.98, I know that this area here, everything greater than that, is 0.025 or 2.5%. Okay, so the way that we're going to cache this piece of information in is by using the Z distribution. And why am I going to do that? Because Z is a known distribution. It has a mean of 0 and a standard deviation of 1. Why is it so important? Because any normal distribution I can transform into Z. It turns out that Z is the same. If I take any normal, so L, take away its mean and then divide by its standard deviation, I get Z. This is so important, and I'm going to show you why. let's write down this piece of information in terms of kind of probabilities. What it says is it says that the probability that I take some L and it is greater than or equal to 50.98, remember probability is represented by area. So that is going to equal 0.025, okay? Now, it's a bit problematic to use my calculator, you know, when I'm putting in the inverse normal distribution and the normal distribution. I need to put in all of my parameters. I need my sigma, I need my mu. So it's tough. If mu is my unknown, I'm kind of stuck with this. I can't rearrange it on my calculator to get probabilities and stuff. I just need my mu. However, this is the power, isn't it? Because with Z, I know my sigma and I know my mu. But then because I can do this transformation to get Z, I can turn this into a Z and then go to my calculator. So let me show you what I mean. This is an inequality, right? So I'm allowed to do the same thing to both sides of the inequality, you know, as long as I'm not multiplying by a minus or anything. So I'm going to take mu from both sides of this and divide by sigma. So I'm just going to literally do the same thing to both sides. So I'm allowed to do that, aren't I? That's just rearranging equations and inequalities. Meaning that I'm allowed to say this, aren't I? That's legitimate. I've not done anything crazy. All I've done is I've said, take away mu, divide by sigma. Inequality still holds. But isn't this thing here equal to Z? It is. So I now know that the probability that Z is greater than 50.98 minus mu over sigma, which we do know to be 0.5, don't we? That's going to equal 0.025. Now this is important because if I was to sketch Z, there is something that my calculator can give me. My calculator can give me, right, here's a distribution. You give me an area. So you give me, for example, this whole area. This is what my calculator does. It goes, okay, this area is something. It's 0.9, right? If you tell me this area, so my calculator is going to give me the value at which this area ends. So for example, I could say to my calculator, you know what, mate, give me the value, this Z value here, such that the area to the left of it is 0.975. Why would I want to do that? Well, if the area to the left of it is 0.975, then isn't the area greater than it 0.025? It is, right? So here's what I can do. This is the Z value I'm after. Because look, I'm looking for the probability that Z being greater than some value is equal to 0.025. That is this value here, isn't it? So what I'm going to do is get that value from my calculator and I can set it equal to this. Okay, so first of all, we know that whatever value my calculator is about to get me is going to be equal to this Z value here because of this setup. And then I'll have an equation for mu. So I'm going to go to menu. I'm going to go to distributions. I'm going to go to inverse normal because we've got the area and we want the Z value. That's the inverse. The area is 0.975. The sigma is 1 because it's the normal Z distribution. The mu is not. And they're usually already in your calculator as that because this is a very standard thing. Press equals. My Z value is 1.95996. ... whatever. Cool. The reason I've not rounded that yet is because I'm going to use it in future calculations. So let's rearrange this, okay? Bring the 0.5 up. So 50.98 minus mu equals 1.95996 times 0.5. Add mu to both sides, and I'm going to be really lazy here. So what I'm going to do is this mu is coming over here, but then I'm taking away this. So what I'm going to do is go... Oh, here we go. You're going here. You're going here. Don't need a plus sign anymore. That is lazy maths right there. So now I can just put this into my calculator, can't I? So go back to the normal mode. Do 50.98 minus 1.95996 times 0.5. And that is going to get you... Okay, it's going to get you so close to 50, isn't it? It's going to get you 50.00002. I'm saying that's 50. I'm saying that's 50. String me up, right? I've got my mu. So now let's retrace our steps because there's a lot still going on. We initially said we've got this distribution. we now just know the mu for this distribution, but we've still got some work to do. So it's now going to be distributed with a mean of 50 and a standard deviation of 0.5. Okay, now what are we being asked? We're asked for the probability that a randomly chosen strip of metal can be used. And this says, so strips with either less than 49 or greater than 50.75 cannot be used. So which kind of makes sense. It's like, you know, you kind of want them to be 50. And you're saying, look, if they're this small, if they are, you know, if they're anything lower than here, I can't use them. That's red zone. But equally, you don't want them to be too long, right? So if they're any bigger than 50.75, I also can't use them. So what I want is this Holy Land right in the middle, okay? So that is basically just the probability that L is greater than or equal to 49 and less than or equal to 50.75. And this, we can use the calculator because we've got mu, everyone's a winner. So I'm going to go distributions. I'm going to go normal CD. My lower is going to be 49. My upper is going to be 50.75. My sigma is going to be 0.5. And my mu is going to be 50. Straight in, I get my answer as 0.910444 ... Let's go 3 sig fig here, which would be 0.910. 2, 3 sig fig. Oof, tough question, really tough. Part B. 10 strips of metal are selected at random. Find the probability fewer than 4 of these strips cannot be used. Well, we know the probability that one given strip can be used. It's 0.91. So the probability that a given strip can't be used is going to be 1 minus 0.91, right? 1 minus 0.910, which is going to be equal to what? 0.09? Okay. So then what have we got? We know the probability that one of them can't be used. And then it says find the probability fewer than 4 out of 10. That's going to be a binomial, isn't it? Because you're counting, you've got 10 trials. There's 2 options. It can be used, it can't be used. And then you're counting how many successes or failures there are. So you've kind of got this x, which is distributed binomially. There's 10 trials, and the probability of success is 0.09. So what we're now going to do is we are going to work out the probability fewer than 4. So I want the probability that it's just strictly fewer than 4, which if you think about it, is the probability that it's less than or equal to 3. Why have I done that? Because my calculator gives me less than or equals to. It doesn't give me less than. So menu, distribution, binomial CD for cumulative. Variable x is going to be 3. Remember, less than or equal to 3. N is 10. P is 0.09. Straight away, I am getting 0.99116 ... Let's go 3 sig fig. 0.991. Now, in statistics and mechanics, when you get these, you know, numerical answers, you can always kind of think, like, does this make sense? Especially an answer as crazy as this, right? Like 0.991, that is so likely. That's a 99% chance. 99.1% chance of being, you know, of happening. So does it make sense that this probability is so high? Well, I should hope so, right? Look at this. It says 10 strips of metal are selected at random. Find the probability fewer than 4 can't be used. You should really hope that if you have, you know, a company that is manufacturing metal strips, that they're going to have less than 4 defects out of every 10, right? Imagine if they have 4 defects out of every 10. That's 40% of every single strip of metal that they make is wrong. So yeah, you would really hope that the probability of getting less than 4 is massive. I mean, it should be 100%, shouldn't it? You know what I mean? Like, it should be less than 4. So that makes sense. I think it completely makes sense to have a massive probability here. Cool, last part. A second machine cuts strips of metal of length x, where x is normally distributed with standard deviation 0.6. I used x in part B, but whatever. A random sample of 15 strips cut by the second machine was found to have a mean length of 50.4. Stating your hypotheses clearly and using a 1% level of significance, test whether or not the mean length of all the strips cut by the second machine is greater than 50.1. Right, so I've got my x. Okay, this is the new x, not the x in part B now. We know it's normally distributed. We don't actually know the mean. I'm going to write this here, okay? And then we're told standard deviation is 0.6. The reason I'm not writing this is because isn't that what this whole hypothesis test is about? Isn't this the unknown here, right? You know, I'm testing, well, is mu 50.1? Is it greater? Is it less than? So if I was to just write 50.1, well, what would be the point in the test? The other reason is, right, my hypotheses are going to be to do with this mu. So I'm going to have the name of an unknown somewhere. Okay, so H0, let's have a look at this. I'm testing if it's greater than 50.1. So the H0, you know, this kind of generally accepted knowledge is, look, mu is equal to 50.1. And then I come barging in and I go, you know what? I actually think that mu is greater than 50.1. I think that the, you know, that the average length of these strips of metal is greater than 50.1. Okay, so here's the interesting thing. I come along and I do a hypothesis test. Now I take a sample of 15 strips and then take the mean. So my distribution is slightly different because the distribution of the mean of these 15 isn't going to be this. It's also going to be normally distributed with the same mean but a lower variance. And the variance is going to be the variance of the norm of this distribution divided by my sample size. In other words, the bigger the sample, the smaller the variance, which should make sense, right? Because imagine my sample is so big. Imagine my sample is so big that it's the population itself. Then obviously the mean of the whole population is the same as the mean of the whole population. In other words, like, you're not going to vary at all from this, are you? You know, the bigger the sample, the smaller the variance. Another way of thinking about this is, imagine that heights of males in the UK, the average height of a male in the UK, an adult male, is 5'10", okay? Now, what's the probability of you going onto the street and randomly picking someone and those being 6'3", for example, 6'2"? It's not super likely, but it's not super unlikely, right? Like, you could easily see someone on the street that's 6'2". So think about that. And then think about the probability of you picking 10 random people from the street, and then the average of all of those people's heights being 6'2". That's unlikely. You know, if the average is 5'10" here, then you're going to get some people, like, it's quite easy for you to get someone above. But then to get 10 people all above, super unlikely. In reality, you're going to have someone there, maybe someone there, another couple here, someone there. The more you have, the closer the average is going to get into the mean. That's the point of a mean. It's an average. In other words, bigger the sample size, the lower you are going to variate from the mean, the smaller the variance. So that's super important there. Okay, so what we're going to do with that, we're then going to say, right, you know, if this mean was the case, so if, you know, H0 were true and the mean was 50.1, what would be the chance of me taking this sample and getting the result that I did? The result that I got was 50.4. So that's here somewhere, right? We can work out the probability of me getting a result over here. If that probability is so small, then maybe I'm thinking, well, you know what? If you were right and the probability, you know, if you were right and I got this result, then the probability of me getting that result was like 1% or something so small. You might be thinking, well, you know, was that a freak coincidence or were you just wrong in the first place kind of thing? So what we're going to do is we're going to work out this probability. So with this distribution, well, with the distribution now assuming that they're correct, so if we have a distribution, if we have a normal distribution with a mean of 50.1, and then, now what I'm going to do is I'm going to write this as one number squared, because that's the number I'm going to put into my calculator. So I'm going to do 0.6 divided by the square root of 15 squared, Because then when I square it, I get that, don't I? So I'm going to work out the probability that this thing here is greater than or equal to 50.4. And then I'm going to check that against my significance level, because that's, you know, what I care about here. Okay, so I'm going to go to distribution, normal CD again. My lower is going to be 50.4. Upper, again, something massive because it's going to infinity, so stick a load of 9s in there. Sigma is going to be 0.6 divided by the square root of 15. And my mu is going to be 50.1. Okay. And then I get this probability to be 0.0264, okay? Meaning that this probability in red is 0.0264. So, I mean, it's not very likely, but it's not that unlikely because my significance level is 1%, meaning that my significance level is actually much further here. You know, it's this here. So, my critical region is everything over here. I'm not yet in the critical region. This isn't unlikely enough for me to think, oh, you know what? Maybe the mean actually is greater than 50.1. So my test statistic in this case does not lie within the critical region. Therefore, there is insufficient, basically. Insufficient evidence at the 1% significance level to reject H0. Very tough ones, normal distribution hypothesis testing. There's a lot going on there, but there we have it. Question 4, what we got? Given that the probability of A is 0.35, probability of B is 0.45, and the probability of A and B is 0.13, find the probability of not A given not B. Alright, mate. So, you don't know the formula for conditional probability, you ain't getting anywhere. So, this formula, mate, you need it. Stick it on your wall, do everything. Just make sure you know this formula, because that's it. As soon as you have this formula with conditional probability, it just turns into normal probability, right? So, in this case, the probability of A dash given B dash would just be, just swap the A here with an A dash and the B with a B dash, right? So it would be the probability of not A and not B over the probability of not B. Cool. I think the bottom's quite easy to work out. For the top, what I'm going to do is I'm just going to draw a bit of a Venn diagram, okay? I feel like it's going to help us visualize what's popping off here. So let's try and fill a bit of this in. If this was A and this was B, now, the probability of A and B is 0.13. Well, that's this bit in the middle. Now I can work out these other bits, because the whole circle of A is going to be 0.35. So if I was to do 0.35 minus 0.13, that's going to get me this bit, which is 0.22. Same thing with B. So if I did 0.45 minus 0.13, that's going to get me 0.32. So this is kind of sweet, and there's kind of something else going on. There's, you know, there's the whole thing, which is maybe a rectangle, right? So then we can say, well, okay, what we want is not A and not B. That's just going to be whatever's outside, isn't it? If you're saying, right, you can't have A and you can't have B either, you've got to be stuck on the outside. So everything adds to 1. So if I do 1 minus 0.22 minus 0.13 minus 0.32, I'm going to get 0.33, and that's the stuff on the outside, isn't it? So this is going to be 0.33 on top, and then the bottom is just not B. So not in this circle is going to be this and this. So it's going to be 0.22 plus 0.33, which is 0.55. You could have also got not B from doing 1 minus 0.45, which is the probability of B. Okay, sticking this into your calculator, I am going to get a nice 3/5 or 0.6. Sick. Part B. Explain why A and B are not independent, right? Well, the condition for independence is the following. For independence, we require the probability of A and B to be the same as the probability of A multiplied by the probability of B. If this is not the case, they ain't independent. So just work them out, right? So the probability of A and B, well, we know actually we've been given it as 0.13. the probability of A multiplied by the probability of B is going to be 0.35 multiplied by 0.45, which I'll tell you, mate, is 0.35 times 0.45. It's going to be 0.1575. So we can clearly see that this is not equal to the probability of A and B. Therefore, they are not independent. Easy as that. Again, you really just need to remember the condition for independence there. Right, part C, let's see what we have. The event C has the probability of C being 0.2. The events A and C are mutually exclusive, and the events B and C are statistically independent. Okay. Draw a Venn diagram to illustrate the events A, B, and C. Ah, you know what? We can use this because C doesn't actually interfere with A because they're mutually exclusive, meaning that they can't happen together. So there will be no intersection with the C circle and the A circle. So if I stick the C circle on here, we are going to need to amend some probability. This isn't going to be the same. This ain't going to be the same. Let's get another circle down here for C. These are going to be the same because the addition of the circle C does not affect the A probabilities at all. Because remember, they're mutually exclusive. It's just some other event that A doesn't care about. So let's work out all of these and see what we got. Now, we do have a piece of information. B and C are statistically independent. So what that's going to mean is that the probability, well, this thing here, isn't it? We're told they're independent. So we're told that the probability of B and C is the same as the probability of B multiplied by the probability of C. So I can write this out. It's 0.45 times 0.2. Straight to the calculator to get me 0.09. So I think they're now going to fall like dominoes, right? So if this is 0.09, then we can write this out because the total circle of B is 0.45. So 0.45 minus 0.13 minus 0.09 gives me 0.23. Same thing here, the whole circle is 0.2. So if I did 0.2 minus 0.09, I'm going to get 0.11. Are we done? Not quite, because there's still this bit on the outside. So everything adds to 1, so do 1 minus all of this stuff here, and it should sort us out. So 1 minus 0.22 minus 0.13 minus 0.23 minus 0.09 minus 0.11 0.22. Thank you, good night, much love. So that, I reckon, is enough for part C. Okay, part D looks a bit grim. However, I don't think it's going to be grim. And the reason is, once we've got Venn diagrams, it's quite easy to get probabilities. So what are they asking for in words here? Basically, this is saying the probability of not B or C. In other words, that's saying you can't be anywhere in B or C. You cannot be anywhere in this circle or this circle. So really, the only two things that remain are this 0.22 and this 0.22, isn't it? So basically, the probability that I'm not in B or C is just going to be 0.22 plus 0.22, which is going to be 0.44. Question 5, let's see what we have. A company sells seeds and claims that 55% of its pea seeds germinate. Write down a reason why the company should not justify their claim by testing all the pea seeds they produce. I mean, surely this can't be a question. Well, it can't be this simple, right? I mean, if you test all your seeds, you're not going to have any left, are you? How are you going to sell any? Surely that's the answer. It seems ridiculous, but how else could I answer this question? You test all your seeds, you've not got any left, have you, mate? So don't be doing that. I mean, yeah, that's what I'm going to write. Look, listen, right, if you test all your seeds, you ain't selling any. Ridiculous. I mean, yeah, it's got to be it though, hasn't it? Don't write that in your exam. Now, part B. Okay, let's recover from that one. A random selection of the pea seed is planted in 10 trays with 24 seeds in each tray. Assuming that the company's claim is correct, okay, so 55% of them germinate, calculate the probability that in at least half of the trays, 15 or more of the seeds germinate. Yeah. I've done a disgusting A-level maths questions on this. It's on YouTube. I'll link it. Because, essentially, It's a binomial within a binomial. So these are quite difficult. Now, I'll go through it now, obviously, but if it's a bit confusing, I go through it in more detail in that video. So here's what's kicking off, yeah. I've got trays. You know, each of them has a load of seeds. 24 of them, to be exact. The seeds here form a binomial distribution, don't they? Because there's two things that can happen. They can germinate or not. And then I've got a fixed number of trials. I've got the amount of seeds in the tray, which is 24. So the probability of germinating is 0.55 because we're assuming that the company's claim is correct. So what I can do is I can say, okay, well, what is the probability that 15 or more of these seeds germinate? And that's binomial, isn't it? Now, my calculator only gives me less than or equal to binomial probabilities because I've not got one of them really posh ones. So I'm going to do 1 minus the probability that x is less than or equal to 14. So now what I do is get to my calculator, go to Menu, Distribution, Binomial CD for cumulative distribution, Variable, stick your numbers in. X is 14, N is 24, and P is 0.55. Put that into the calculator, and I'm going to get 0.70087. Okay, just, you know, I'm not rounding loads just yet, just because I'll only do that in my final answer. So back to normal mode, work this out. So 1 minus 0.70087, that gets me 0.29913. Sick. Okay, I'm not done yet though, am I? Because I don't just have one tray. So this is the binomial within a binomial bit. I've got another tray, and I got another tray, and I got another tray. I've got 10 of them, haven't I? So here's the thing. Yeah, inside a single tray, there's a binomial. But then I'll zoom out and see all of the trays, and all of those form another binomial, don't they? So I've got another binomial y. It's got 10 trials because there's 10 trays. And then what are we defining as success in a given tray? In a given tray, success is at least 15 of the seeds germinating. So we've worked that out because that is 0.29913. So now what I want is I want the probability that this happens in at least half of the trays. In other words, the probability that y is greater than or equal to 5. Kicking off, innit? So again, 1 minus p that y is less than or equal to 4. And then get it from your calculator. So back to the menu. Distributions. Binomial CD. Variable. X is going to be 4. N is going to be 10. And P is going to be this 0.29913. Stick that in your calculator and I get 0.851219 ... That's probably enough. Now finally go back to the normal mode. 1 minus all of this, 851219, and I get 0.14878 ... Let's round this to 3 sig figs, so 0.149 to 3 significant figures. Whew, binomial within a binomial. Again, discussed in any other maths questions, go watch it. Cool. Part C. This is just something you need to remember. I've explained it in other videos, so I'm not going to do it now fully, but essentially, you need n to be large. So, if a binomial has loads of trials, good, and if the probability of success is close to a half. Because remember, normals are symmetrical. So you're only going to get kind of a binomial that has a symmetrical distribution if p is around a half. If p is like 0.01, it's going to like peak here and then go flat. So it's not going to be symmetrical. So n large and p close to 0.5. Fantastic. I've fully gone through why this is the case on AITutor. I'm not going to do it here. Okay, so part D says a random sample of 240 pea seeds was planted and 150 of these seeds germinated. Assuming the company's claim is correct, okay, so the 55% thing, use a normal approximation to find the probability that at least 150 pea seeds germinate. Okay, so in terms of the binomial that I have here, right, I've got a binomial distribution because they can either germinate or not. I've got 240 trials, And then the probability of germination is 0.55. But now I'm using this to get a normal, aren't I? And then the normal approximation is basically mu equals NP, sigma squared equals NP times 1 minus P. And I know I can use this. 240 is large and P is close to 0.5. Okay, so mu is equal to NP, which is going to be 240 times 0.55. Let's work this out. 240 times 0.55 gets me 132. Sigma squared is NP times 1 minus P. So that is going to equal, well, we know that NP is 132 times 1 minus 0.55. Okay, so answer times by 1 minus 0.55 is going to get me 59.4. Meaning that's my normal, you know, the normal approximation to this is going to be normal with a mean of 132 and a sigma squared of 59.4. So a little trick that I like to do, remember normals are mu and sigma squared. So you might get confused here because you actually kind of want sigma here. So I actually like to do, you don't have to do this, but what I like to do is write this as the square root of 59.4 all squared, because that's how we generally write normals. We write mu and sigma squared. So now we know what our sigma is. It's the square root of 59.4. You know, you might be fooled into thinking that sigma is 59.4 when you put it into your calculator, you losing them marks. So what do we now want? We want to find the probability that at least 150 pea seeds germinate. Okay, so you might be thinking, well, now we just need the probability that, you know, this y is greater than or equal to 150. Not so fast. And the reason is we need to use what is called a continuity correction. Let's think about those words, right? What are we doing? We've got a binomial, which is a discrete distribution, and we are approximating it with a normal, which is a continuous distribution. So something bad's happened, hasn't it? We've gone from discrete to continuous, which obviously isn't, you know, perfectly mathematically correct. So we need to kind of correct for this. So let's have a think. I'm going to draw a line for you, right? So in terms of the discrete distribution, you know, we know that it can only take on integer values. 148, 149, 150, 151, 152, okay? This is a discrete distribution. So if this was a binomial, we would be like, okay, sweet, well, that's just going to be everything, you know, over here, isn't it? It's going to be greater than or equal to 150. Problem is, we've got a normal, haven't we? So, you know, whereas I know that the binomial can only take these jumps, it can't be anywhere here, the normal can. So, given that the normal can actually take a value here, it can take a value here, it can take a value here, it can take a value here, etc. There's actually going to be more values that I'm going to want to, you know, use here. Because, you know, one thing that we could say is, okay, we're using a continuous to, you know, approximate a discrete. So if I get a value, you know, that's not an integer, it's not a whole number, I'll round it. So you might say, okay, if I was to get a value of this here, which is, you know, 149.8, I'll round it to 150, which makes sense, right? You would, wouldn't you? Because you know it can't be between 149 and 150, so you'll round it to the closest integer. So here's the thing. When we're doing the normal probability, we're going to need to take account, you know what? There are actually more values that are going to round to a number greater than or equal to 150. Because if you think about it, here is 149.5. If I had a value greater than or equal to 149.5, when I then rounded it, I would get 150 or greater, wouldn't I? You know, if I was 149.4, I'd round to 149. But 149.5, I round it, I get 150. Anything greater than it is going to round to a number that is at least 150. So what I actually do is I work out the probability that y is greater than or equal to 149.5. That is a continuity correction. Okay, at this point, I can stick some numbers in. So it's just normal probabilities, isn't it? So I'm going to go menu, distributions, normal CD My lower is 149.5. My upper is just something massive, smash the 9 button, we know the way. Now my sigma is going to be the square root of 59.4. My mu is going to be 132, press equals. And this is going to get me 0.01158. And let's round to 3 sig fig. So this is going to be 0.0116 to 3 sig fig. Fantastic. Using your answer to part D, comment on whether or not the proportion of the company's pea seeds that germinate is different from the company's claim of 55%. Okay. Right, yeah. Here's the thing. We're saying, okay, assuming, what did we do in part D? We said, assuming that the company's claim was correct. So, you know, in part D, I'm going to write out what I'm saying, okay? So in part D, we assumed that, you know, 55% germinate. That was the company's claim. And we used that information to work out the probability that at least 150 germinate, okay? So we assume that 55% germinate. We then found that the probability of at least 150 germinating was really low. It was 0.0116. That's 11.6%, right? No, it's not. It's even lower than that, isn't it? It's 1.1%. It's about 1%. 11%. So that's super low, isn't it? About 1%. So here's the thing. If the company was telling the truth, the fact that 150 seeds germinated, there would have been a 1% chance of that happening. So do you either think that we got this freak 1% result, or do you think that the company was just kind of chatting a bit? You know what I mean? So this claim really, you know, it doesn't seem to add up. It would be like, if it was correct, it would have to be a freak 1 in 100 thing that happened. So I would say, look, part D, we assume that 55% germinate. We then found that the probability of, you know, at least 150 germinating was about 1%. Very low probability, wasn't it? So I don't think this really supports, you know, I think that there's evidence that the company's incorrect claim, right? So very low probability. So there is evidence that the company's claim is incorrect. That's not you. That's the plural of companies, isn't it? Come on, companies. There we go. English lesson and all. You get it all at AITutor YouTube channel, right? I think that'll do it for stats. All right, now we're getting into the good stuff. Stats is over, so we can rejoice. Let's have a look at what we have. Unless otherwise indicated, whenever a numerical value of G is required, take G as 9.8. Sweet. Give your answer to either 2 significant figures or 3 significant figures. Nice. Okay. So yeah, this is a classic, right? Take G as 9.8, unless the question says, you know, take G as 10, for example. All right, let's have a look. At time t seconds, where t is greater than or equal to 0, a particle P moves so that its acceleration A is bold, which means it's a vector, is given by 5ti minus 15t to the half j. When t is 0, the velocity of P is 20i. Find the speed of P when t equals 4. Okay, couple of things popping off here, isn't there? So, I think the first thing we need to think about is the relationship between acceleration and speed, or actually acceleration and velocity. So, the relationship between kind of all of them, right? I've got my displacement, we can call it R, we can call it S. Differentiate that, I get my velocity. Differentiate that, I get my acceleration. So this way is differentiation, which means this way is integration, right? So if I have acceleration and want velocity, I need to integrate. In other words, the velocity is going to be the integral of my acceleration. So it's going to be the integral of 5ti minus 15t to the half j dt. Sweet. So kind of two separate things here, right? There's some I and some j. So what I'm actually going to do is, right, okay, I integrate 5t. I'm going to get what? I'm going to get 5t squared over 2. Now, the reason I'm hesitant here is because there's going to be a plus c somewhere, but we need to actually be careful about where that is. Because I'm going to have 5t squared over 2 here, and then there's kind of going to be some I here. And then what have I got in terms of the j? I've got minus, so add 1 to the power, I'm going to get t to the 3 over 2. The 15 is still chilling, and then divided by 3 over 2 is the same as times in by 2 over 3, so it's going to be like that. And there's some j there. It would be incorrect to just write plus c on the end. Because look, these are vectors. So I can't have these vectors added by a scalar. So you kind of got two options. Either the c itself is a vector, or there's two separate parts of c. So either is okay. But I'm going to do it as two separate parts. So I'm going to say that there's some kind of I component of c, which is obviously in the I direction, and then some kind of j component of c in the j direction. Okay. Let's just clean this up, and then I think I'm good for now. So can't really do anything to this, kind of. So that's just going to be 5t squared over 2 plus ci lots of I. And then minus, look at this, 15 and the 3 cancel nicely. 15 over 3 is 5, then I'm still timesing it by 2. So I've got 10 to the t3 over 2. Now I'm writing plus cj here. You could write minus cj. Technically this would mean minus when I multiply the bracket out, but it doesn't matter, does it? Because it's an arbitrary constant, I can define it how I want. Okay, so obviously we have these constants. How do we get rid of them? So that is usually when they give you a piece of information. So look at this. It says, when t is 0, the velocity of p is 20i. In other words, I can now sub in t equals 0 and sub in 20i for the velocity. So v is this, so now I'm going to get 20i equals, okay, t is 0, so this goes chow. I'm going to be left with ci lots of I. And then this here goes chow, so that's going to be minus, gone, cj lots of j. We can now compare the i's and the j's here. Now, there's no j here, is there? Meaning that this cj must be 0, right? The j component of the velocity when t is 0 is 0. So straight away I know that cj must be equal to 0. And then look, I must have 20 lots of I is equal to ci lots of I. In other words, ci is 20. Okay, pues que tenemos ahora, what we have is we have the velocity is equal to, and then just this that we have here, and just sub your constants in, so you've got it nicely there. So it's going to be what? It's going to be 5t squared over 2 plus 20 lots of I, and then minus, this has gone now, isn't it? So 10t to the 3 over 2 lots of j. Okay. What's the final question? It says, find the speed of p when t is 4. Well, sub t equals 4 in, right? So what am I going to get? I'm going to get 5. So I'll say when t is 4 here. Because it wouldn't be right to say that that's just equal to this having subbed in 4, would it? So 5 times 4 squared over 2 plus 20 lots of I minus 10 times 4 to the 3 over 2 lots of j. Now I could try and impress you here by doing it without a calculator, but I would rather not encourage that behaviour because you ain't impressing anyone, so let's just go to it, right? So first thing I'm going to do is I'm going to write 5. I'm going to have a bracket and then write 5 times 4 squared over 2 plus 20, which is going to get me 60, so that's 60 lots of I. And then I'm going to write 10 times 4 to the power of 3 over 2, and that's going to get me 80, so that's going to be minus 80 lots of j. Am I done? No, because there is a difference between velocity and speed. Velocity is speed with the direction, so what this velocity is saying is, for in a given second, I am travelling 60 in the I direction, and then minus 80, so I'm going down by 80 in the j direction. But speed doesn't care about that. Speed just says, what is your, what is the size of this? How fast is it? What is the magnitude of this speed? That is always given by the resultant, right? So all the speed cares about is, look, I'm doing this much in this amount of time. How am I going to work this out? Our good old friend Pythagoras, right? So all this is just going to be the following. Speed is going to equal the square root of 60 squared plus 80 squared. And I think we know what to do now. So square root 60 squared plus 80 squared, which gives us a cool 100. And then this is going to be what? Meters per second. All right, what we got here? A rough plane is inclined to the horizontal at angle alpha, where tan alpha is 3/4. A particle of mass m is placed on the plane and then projected up a line of greatest slope of the plane. Okay, coefficient of friction between the plane and the particle is mu, and it moves up the plane with a constant deceleration of 4/5g. Okay, find the value of mu. Woo! They're just throwing us in, aren't they? 6 marks. Right, you're not going to have a clue what's going on here if you don't draw a diagram, right? And if you do, you're cleverer than me. So I'm going to draw a diagram. So basically, they're always going to look the same with these inclined planes, yeah? We've got a line. We know the angle at which it is inclined, which is alpha. And then, you know, what have we got? We've got some particle, so let's stick in A. And then what are the forces acting on this particle, okay? So what are we always thinking? We're thinking weight always acts downwards. Straight down towards the earth. It doesn't matter, you're inclined, you're going down towards the earth. Weight is equal to mass times gravity, and mass in this case is m, so mg. What else do we have? We always have a reaction force, and the reaction force always acts perpendicular to the plane, so coming out of the plane like this. Cool. And I don't really know exactly what it is yet, so I'm just going to write R. Now, something that I always want you to do, right? Always, always, in the inclined planes, is draw a dotted line here. Because this angle between this is always going to be alpha, okay? I'm not going to prove that to you now, because I can't be bothered. But it is, okay? So this is going to be useful, because I'm going to want to resolve this weight kind of in that direction of the dotted line. So that's going to help me later on. Okay, what else do we know? Well, look, it's projected up the plane, so it's currently kind of moving up the plane. So if it's moving up, what is the direction that friction is going in? Well, friction is opposing motion, isn't it? So friction is going to be going down the plane. So I have an F going down here. Cool. Do I have any other forces? I don't think I do. So, you know, it's projected up. So, you know, you might think, well, what's the force taking it up? Like, it's initially obviously going to have some force to project it up, but then that's it. And you can see that, you know, it is decelerating. So as it stands at the moment, there's no force pushing it up. You know, it's still got a bit of that velocity from before, so it's moving up, but it is eventually going to kind of come to a stop and then maybe fall down again. So there's actually nothing taking it up here. Okay, I believe that's kind of all the information, you know, I need to get on this diagram as it stands. Okay, quick little note about alpha now. I've spoken about this in other videos, so I'm going to go through it quite quickly. I'll try and link it to you if I remember. But essentially, instead of giving us alpha, they have told us that tan alpha is 3/4. Why have they done that? Because they want us to notice that if I was to draw a right angle triangle and use SOHCAHTOA, if this was alpha, for example, then TOA, tan alpha, is the same as opposite over adjacent. In other words, opposite over adjacent. So that's going to be 3/4. Using Pythagoras, I can then work out the hypotenuse, which would be 5. So basically, I can get sine alpha and cos alpha without actually working out the value of alpha. And this is good, because the value of alpha would just be some horrible decimal. You'd start introducing rounding errors, bad times, okay? So sine alpha is going to be opposite of a hypotenuse, so 3/5. And cos alpha is going to be adjacent over hypotenuse, so 4/5. So then you can kind of park that for later, can't you? Something just fell out of my mouth, that was grim. Okay, what do we need to do now? So it's basically now the arrows, isn't it? We're resolving forces, we're doing all of that fun stuff. So in perpendicular to the plane, it's not accelerating. Perpendicular, it's in equilibrium, isn't it? Because it's not flying upwards and it's not going into the plane. In other words, everything taking it up this way, it's going to be balanced by everything taking it down that way. So, well, what's that going to give me? Well, that's going to give me R, because that's what's taking it that way, is equal to mg and then cos alpha. And the reason it's cos alpha is because to get from the line mg to the dotted line, I go across the angle. If I go across the angle, I use cos. So it's going to be mg cos alpha. Okay, let's park that. You know, we can actually simplify this, so let's do that first. We know that cos alpha is 4/5, okay? So this is actually going to be 4/5 mg. Fantastic. And then there's obviously the other direction remains. So it is accelerating in this other direction, isn't it? So that it's not an equilibrium, we're going to need to use F equals ma. So what we can say is we can say that, you know, everything pulling it up minus everything pulling it down is equal to its acceleration, okay? So everything pulling it up is going to be, you know, taking it that way, minus everything pulling it down, because that's going to be the resultant force upwards, is equal to the mass times the acceleration. Okay, everything pulling it up, well, there's actually nothing there, is there? So nothing is pulling it up, but there are things pulling it down. There's the F is pulling it down, so we'll get that in. So there's going to be nothing, essentially, minus F, but then there's also the component of the weight acting down the plane. So the component on the dotted line was mg cos alpha, so the other one is going to be sine, so it's going to be mg sine alpha. And another way of thinking about that is because I'm going away from this angle. So I'm going to get minus mg sine alpha here. Starting to kick off now, innit? And then that's going to be equal to m, and then what is the acceleration here? Well, we're told that it moves up the plane with a constant deceleration of 4 over 5g. So in other words, the acceleration is going to be minus 4 over 5g. And it's at this point where we try and do some maths. Okay, so first thing I'm noticing is that I know what sine alpha is here. It's 3 over 5. So let's stick that in there. I'm going to have minus f minus 3 over 5 mg is equal to, what's that going to be? It's going to be minus 4 over 5 mg. So this is quite nice because we are seeing that these are kind of the same term. We can use something else though, can't we? Because f, what is f equal to? Well, you best remember this because it is equal to mu times r. R being the reaction force and mu being the coefficient of friction. Now technically it's f is less than or equal to mu r, but because it's moving, we know that friction is at its maximum. In other words, friction is equal to mu r. So what is mu? Well, mu is just mu. We don't know it yet. So we're going to have mu, but we do know what r is because we've already worked that out. That is 4 over 5 mg, isn't it? So we get minus mu times 4 over 5 mg. So let's stick this here. Minus 3 over 5 mg is equal to minus 4 over 5 mg. Sweet. So looks a bit grim, but loads of things cancel here. There's an mg in everything. So I can say chow, 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 get rid of all of those. So what am I left with? Minus 4 mu over 5 minus 3 over 5 equals minus 4 over 5. So this is okay at this point, isn't it? Let's multiply by 5. Why not? So I get minus 4 mu minus 3 equals minus 4. There's a lot of minuses. Why don't I multiply everything by minus 1? Just flip the signs, okay? So I get 4 mu plus 3 equals 4. Take the 3 over to the other side to get 4 mu equals 4 minus 3, which is 1. So mu is equal to a nice quarter. That's quite good, isn't it? Sweet. The particle comes to rest at the point A on the plane. Determine whether the particle will remain at A, carefully justifying your answer. Okay. So here's the thing. Once it comes to rest, there's a bit of a different situation going on. Anytime the forces change or, you feel like there's a difference in the model and the movement, draw another diagram because it's going to be completely different. So these questions happen a lot, right? There's a lot of the force X is now removed. Tell me something. You're going to need another diagram because, the whole mechanics of the problem are going to be different if one of the forces is taken out. So let's do the same thing and have a think about if it would be any different in this case, okay? So let's go blue, right? It's different. So obviously, the plane hasn't changed at all, has it? And I've still got a particle here. It's still got a weight. I still do my dotted line. Yeah, you haven't forgot that one, have you? There's still a reaction force. But now there might be some differences. Because in part A, the particle was moving upwards. Meaning that friction, which was trying to oppose the motion, was trying to say, whoa, 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 pull it down. But in this case, what is the particle's kind of natural course of action? What does the particle want to do, looking at this? Well, does it want to go up the plane? I don't think it has a reason to. There's no arrows going upwards. It wants to go down, doesn't it? Because its weight is trying to pull it down the plane. So friction now, it's going up, isn't it? It's saying, whoa, 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 you're trying to go down here. I'm trying to keep you up, mate. Okay? So friction is going upwards. So let's think about it here. The question is basically broken down into, okay, well, is the maximum friction big enough to stop this thing going down the plane? Because you've got two forces fighting now, haven't you? You've got a bit of the weight pulling it down, and you've got the friction trying to keep it up. If the bit of the weight trying to pull it down is bigger than the maximum friction, then friction won't be able to do anything else and it comes down. But if it's smaller, then the friction's actually strong enough to just keep it still. So here's the thing, the maximum friction isn't going to change at all. And the reason is because friction is equal to mu r, isn't it? Or F max is equal to mu r, should I say. But nothing in the direction of the kind of reaction force has changed since last time, has it? F was equal to mu r last time, and it's still equal to mu r here. Because, okay, the friction has changed direction, but in terms of, R's not going to be any different from last time, is it? And mu isn't different, because mu is just to do with the actual, materials of the particle and the surface. In other words, max friction is the same as it was last time. And max friction last time was this, wasn't it? It was 4 over 5 mu mg. So F max is still 4 over 5 mu mg. And we actually know the value of mu now, don't we? It's a quarter. So this is going to be 4 over 5 multiplied by a quarter mg. That 4 cancels with that to get a fifth mg. So now the question is, okay, well, is this weight bigger than a fifth mg? If it's bigger than a fifth mg, then the friction isn't going to be strong enough and it's going to fall down, okay? So remember, this is alpha still, meaning that the weight trying to take it down here, okay, that's the component of the weight going down there, is equal to what? It's equal to mg sine alpha. And what did we say sine alpha was? We said sine alpha was equal to 3 over 5, meaning that the force on the particle going down the plane is 3 over 5 mg, which is greater than F max. Therefore, the particle will fall down. So, component of weight going down the plane is greater than the max friction, so particle will fall down. And that will hopefully do the job for question 7. Let's see what's popping off with 8. A radio-controlled model boat is placed on the surface of a large pond. Of course it is. The boat is modelled as a particle. Time t equals 0, the boat is at a fixed point O, origin, and is moving due north with a speed of 0.6. Relative to this origin, the position vector of the boat at time t seconds is r meters. Time t equals 15, the velocity is that. The acceleration of the boat is constant. Show that the acceleration of the boat is 0.79 minus 0.1 j meters per second squared. Okay, I can understand if a student would be kecking it at this point, right? They've just read 7 lines of just English, and it's like, what? How am I going to process this information? It's just sentence after sentence of, this is something else you need to think about. So let's chill out. Yeah, chill out. I'm looking at this sentence here, the acceleration of the boat is constant. So instantly that's telling me, right, that we can use Suvat equations. Because what are the Suvat equations? They are the equations of motion with constant acceleration. So it's like constant acceleration, Suvat equations. So what I would do is I'd write my Suvat out, right, SUVAT, and then just see if I can pick off these bits of information, stick them into the Suvats, right? So here we go, I've got Suvat. Now these are going to be vectors now, because look, I'm working in 2 dimensions, i's and j's. So Suvat, so underline for a vector, they're probably not going to go mad at you if you don't, but I think it's a good habit to get into. Now, you might see this given as r. I've explained this in another video. S and r are basically the same thing, because if you think about it, if I have some origin, and r is my position at a certain time, say here, for example, well, what does the displacement ask? Well, this r is the position relative to the origin, but the displacement asks, well, how much have I displaced from this origin, right? So if my position relative to the origin is 3, 4, well, then I've also displaced from the origin 3, 4. So it doesn't matter, right? I'm going to use S. If you want to use R, don't worry about it, okay? So S, in this case, what I'm going to do is, you can see that they give us this 15-second window. Let's try and apply the suvat to that. Don't think it tells us anything about its position or displacement. Does it tell me the initial velocity, u? I think it does, because it says at time t equals 0, the boat is at a fixed point O and is moving due north with a speed 0.6. Well, due north, remember, i's and j's, so 0.6 north is 0.6 j, isn't it? V, do we know this final velocity? We do, because it says at time t equals 15. The velocity of the boat is 10.5i minus 0.9j. Sick, okay. Do we know anything else? Acceleration's constant, find acceleration. Well, we've got enough info now, haven't we? If we want acceleration, we can use the suvat that relates these. And luckily, it's El Clásico. It's the v equals u plus at. It's the one everyone can remember because it's easier, right? So if we use v equals u plus at here, what we're going to get? We're going to get 10.5i minus 0.9j is equal to u, so 0.6j, plus at, so plus 15, which is t, lots of a. Rearrange for a, right? So take the 0.6 over to the other side. So I'm going to get 10.5i minus, so minus 0.9 minus 0.6 is going to be minus 1.5. It's going to equal 15a. Divide by 15 and we're sweet, right? So a is going to be 10.5 over 15 lots of I minus 1.5 over 15 lots of j. Now, I have already mentioned that I have no interest in impressing you with my mental math skills, so I'm going to do 10.5 over 15, which is going to get me 0.7. And then, well, 1.5 over 15 is going to be 0.1, isn't it? So hopefully the answer is 0.7i minus 0.1j, and then obviously units are going to be meters per second squared. Cool. Find R in terms of t. Okay, so be careful because they're not asking specifically for this R, because this suvat setup is for when t equals 15. They're just asking for the general R. So, instead of t being 15 there, we would have t equals t kind of thing. So let's write the suvat variables again, actually. It'll basically be almost the same as that there, but just with a couple of differences. So S, again, S, I told you why. You can use R, that's fine. So if we want this in terms of t, we're not going to know v, are we? Because the v that we had last time was specific to when t was equal to 15. So we're not going to know v. Again, t isn't 15 anymore, but t is just our generic t, because it wants its answer in terms of t. We do know the acceleration now, because remember, we're told that that's constant. So acceleration is going to be this. So it's going to be 0.7i minus 0.1j. U is still the same, isn't it? Because, the initial is always the initial, okay? So U is still that, 0.6 lots of j. So then the question is, the question is, how do we speak, mate? Question is, how do we get S now, okay? Well, what is the equation that relates S to U, A, and T? It is S equals UT plus a half AT squared. Stick them in, you should be laughing. So this is going to equal 0.6 T lots of J plus a half times A, so 0.7I minus 0.1J times T squared. So this is technically it, but I am going to simplify it. It's always a good idea to group your I's together and your J's together, because they're independent things, aren't they? So in terms of I, what do I have here? My only I term is actually this old fella here. So this is going to be a half times 0.7 times T squared lots of I. So a half times 0.7 is 0.35. And then I got t squared. Lots of I. And then my j's, right, what do I have? So it looks like I've got 0.6t here. And then I have minus 0.1 times a half times t squared. So minus 0.1 times a half is 0.05. And then I got that t squared. And then remember, all of this is j. So I think that's s or r, whatever you like. Find the value of t when the boat is northeast of O. All right. Northeast of O. It's compass time, orienteering time, mate. Okay, so O is here, isn't it? It's my origin. Northeast, right? So never eat shredded wheat. Sure, you can think of other ways to remember that. I will let your imagination run wild. But essentially, if I've got north, east, south, and west, northeast is perfectly between north and east, okay? So obviously this is 90 degrees. It's going to be perfectly in between here. Just like this. You know, so this is going to be 45 degrees. It's going to be exactly in the middle. So what is special about this line? If you think about this line, if this was like an x, y coordinates, the x and y coordinates are always going to be the same, aren't they? Right? It's like the line y equals x, isn't it? You know, if I go 3 along, I go 3 up because I go as much east as I go north. Meaning that all along here, you know, this point, it could be 2i plus 2j. This point could be 3i plus 3j, etc. What's special? The amount of I is always going to be exactly the same as the amount of j, isn't it? So the point, or points, who knows, at which it is northeast, it's just going to be when the I component, when the 0.35t squared is going to equal the j component, which is the 0.6t minus 0.05t squared. Okay? I've got a quadratic. Let's solve it. So let's get everything onto the left-hand side. That's what I like to do with quadratics. So I'm going to have 0.35 plus 0.05 lot of t squared. That's going to be 0.4t squared. And then I'm going to take that 0.6 away. Right, I've said this a million times. Do not just divide by t here. Factorize it out, yeah? Let's not be losing solutions. So I get 0.4 t minus 0.6. So I get 2 solutions here, don't I? I get either t is 0 or 0.4t minus 0.6 equals 0. So this here, I'm going to add 0.6 and then divide by 0.4 to get t as 0.6 over 0.4. What would that be? That would be 6 over 4, wouldn't it? If I times top and bottom by 10, which is 3 over 2. So I've got 2 answers. They only want one specific value, but let's have a think about it. T is 0 kind of makes sense because at t equals 0, I'm at the origin. So obviously the I is equal to the j because they're both 0. But then, you know, the later time is going to be, so, you know, at t is 0, you're technically not northeast of O because you're at O, aren't you? But then the one time when I am northeast of it is when t is equal to 3 over 2 or 1.5 seconds. So my answer here is going to be 1.5 seconds. Sick. All right, find the value of t when the boat is moving in a northeast direction. Super similar to the last part, but slightly different. Part C says, when is it northeast? Part D says, when is it traveling northeast? So when is it northeast? I care about the position, the displacement. When is it traveling northeast? I need to care about the velocity here. The velocity is, you know, telling me where it's traveling, okay? So if I was to work out the velocity in terms of t, and then do everything I just did there in part C, I should be sweet here. So how am I going to get the velocity? I think I'm going to do this. Because look, the suvat that we care about is this here. So we can use v equals u plus at on this because I've got u and I've got a, okay? So to get v in terms of t, it's going to be u, which is 0.6j, plus a, which is going to be the 0.7i minus 0.1j, lots of t. Group your i's, group your j's, do the same thing. So in terms of I, I've just got this, so I've got 0.7t lots of I. In terms of j's, I have 0.6 minus 0.1t. And again, right, if I'm traveling northeast, the amount of I that I'm traveling has to equal the amount of j. So I'm going straight up here. In other words, 0.7t must equal 0.6 minus 0.1t. What do? Take the 0.1t over to the other side to get 0.8t is equal to 0.6. Divide by the 0.8. 0.6 over 0.8, which is what? 6 over 8. Divide by 2. What do I get? I get 3 over 4, or 0.75. Forgot how to write seconds. And I reckon that that will do the job for part 8. Moments. What we got? Uniform ladder AB of length 2a and weight W has its end A on rough horizontal ground. You know what? Before we read all this, get the diagram up, and as we read it, start adding stuff to the diagram, start getting the information down, because if not, we're going to read this absolute paragraph, and then we're just going to be like, well, what has even happened then? I can't remember anything. But if we kind of chip away at it as we go, then we're cashing that information in, aren't we? So let's do that instead. Look, coefficient of friction between the ladder and the ground is a quarter. Write it down before you carry on reading, right? So mu is a quarter down here. Sick. The end B of the ladder is resting against a smooth vertical wall. Okay, no friction here. A builder of weight W, 7W, stands on top of the ladder. Get it down, right? So is at the top. Our mate here, chilling, and he's 7W down here. Sick. To stop the ladder from slipping, our mate's assistant applies a horizontal force of magnitude P to the ladder at A towards the wall, okay? So there's someone down here pushing it towards the wall. The force acts in a direction perpendicular to the wall, okay? So it's basically going to be going towards the wall, straight like this, perpendicular. So over here, I've got P. Cool. So I'm cashing it in, right? I'm not going to have to read all this again. The ladder rests in equilibrium in a vertical plane perpendicular to the wall and makes an angle alpha with a horizontal ground where tan alpha is 5 over 2, okay? We've seen this before, haven't we? Calculator's fallen over. We'll get it later, right? So tan alpha is 5 over 2. What does that mean for sine and cos? Well, you tell me, right? Because we did it a couple of questions ago, didn't we? If I have this here, and this is alpha, well then tan, which is opposite over adjacent, would mean that the opposite is 5 and the adjacent is 2, right? So if I was to now grab this calculator that has just fallen on the floor and do Pythagoras to get the hypotenuse, what am I going to get? I'm going to get the square root of 5 squared plus 2 squared, which is root 29. Which would therefore tell me that sine alpha, which we know to be so opposite of a hypotenuse is 5 over root 29. And a cos alpha, which we know to be, ka, so adjacent over hypotenuse is 2 over the square root of 29. Cool, carry on. The builder is modelled as a particle and the ladder is modelled as a uniform rod. That's important because uniform means that its centre of mass is in the centre, right? So its centre of mass will be A, distance of A up here, and its weight is W. What do we do when we do this? We do a dotted line here because we know that that's always going to be alpha. Right. Anything else on this diagram? I don't even know what they're asking me yet, but I don't care. Is there anything else to put on this diagram? I think there is. So the first thing we know is that there's friction at A, isn't there? What directions is friction going to act in? Well, think about it. The ladder is wanting to kind of fall this way and send our mate over here to hospital, isn't it? So the friction is going to want to oppose that, just as his assistant is opposing it, right? Or her assistant, we don't know. So we've got P pushing it this way. The friction is also going to be pushing it this way because they want to stop this ladder from slipping. So I've got an F going over here. Okay, so is there anything else? I think there is, because we have reaction forces, okay? So with the reaction forces, they always act, well, they're when something's on a surface, okay? So obviously, the reason that this ladder isn't just falling straight into the earth here is because there is ground there. That ground is putting a force up on that ladder. And reaction forces always act perpendicular to the surface. So the reaction force is going straight up. Let's call this RA, reaction force A. Same with the wall. Why isn't the ladder falling through the wall? Because the wall is producing a reaction force on it, going this way. Again, perpendicular to the wall, I'm going to have RB. Cool. It would be good to kind of look at some angles here. So just as I did here, you know, I could kind of do a bit of this. That's going to be alpha. It would also be interesting to me if I knew the angle here. Now be careful because it might not be alpha. So let's have a think of this. Look at the Z angle here. If this is alpha, then there's going to be an alpha here, isn't there? So that would actually make this 90 minus alpha, but I'm happy with just putting the alpha there because that's enough for me to know when I come on to doing the maths what it's going to be. Right, I think I'm happy with that, but you know, we'll see what they ask and then I might need to kind of change stuff, okay? So the part A just says, show that the reaction of the wall on the ladder, so this RB, has magnitude 3W. Okay, now always think with moments, what are the different ways I can get equations? I can do left equals right, I can do up equals down, and I can take moments. So let's have a bit of a think about those. Up equals down isn't going to work because RB is horizontal, so it's not even going to turn up in the equation. Left equals right, I've got a lot of unknowns, haven't I? Because I got P, which I don't know, I got F, which I don't know, and then RB. So I'd get an equation with 3 unknowns in it. No, yeah, how am I going to work that out? But if I was to take moments, moments are cool because if I take them about a specific point, they just get rid of the variables at that point. For example, if I took moments at A, then I wouldn't have to include RA, P, or F in my equation because moment is force times distance, but the distance here of these forces from A is 0. So I'd do the force multiplied by 0, gets rid of it. So if I was to take moments about A, here's what's going to happen. I'm going to have to balance this force, and this force. They're the only 3 forces that will be in the equation. And it's going to be the total kind of things trying to rotate it this way. So maybe everything trying to rotate it that way is going to be balanced by everything trying to rotate it the other way. Okay, trying to rotate it this way, what am I going to have? I'm going to have this weight here that's trying to kind of pull it down that way. So what's the moment going to be? Well, it's going to be the distance from A to the middle, which is going to be just little a, multiplied by the component going down here of this force, because it's always perpendicular, okay? So it's going to be W cos alpha, because we're going across the angle. So it's going to be AW cos alpha. And then the other thing trying to rotate it this way is this, isn't it? Because, you know, they're going in that same direction. So it's going to be the distance, which is 2A, multiplied by the component of the force taking it this way. So it's going to be 2A multiplied by 7W cos alpha. 2A multiplied by 7W cos alpha. And then they're both balanced by this the moment produced by this RB, because that's trying to kind of take it the other way. So the distance is going to be 2A. And then the component going up here is going to be RB, and then I need to go away from the angle, so it's going to be RB sine alpha. Okay, pretty grim equation here, but let's just see what we can do. Can anything cancel straight away? I think it can, because there's an A here, an A here, and an A here, so that's good. Now, I can see that there's cos alphas and sine alphas. Now, I might be inclined to sub these in. I've got 2 choices. I can try and be clever with trig, you know, using the fact that tan is sine over cos, or I could sub them in. Let's sub them in this case, because I can see some all-right cancellations happening. So I'm going to get W times cos alpha. So 2 over root 29, that's the cos alpha, times W. and then plus 2 times 7w is 14w times by 2 over root 29 equals 2rb times sine alpha, which is 5 over root 29. The root 29s are a bit grim, but I can cancel them all because every term is divided by root 29. So I've multiplied the whole equation by root 29. They'd go. Leaving me with 2w plus 14w times 2, which is 28w, is equal to 2 times 5, so which is 10 lots of RB. Cool. So 10RB is going to be what? 30W. Dividing both sides by 10 is going to get me RB equals 3W. Okay, nice. At least we got one part. Okay, find in terms of W the range of the range of possible values of P for which the ladder remains in equilibrium. This is going to be pretty horrible, isn't it? Right. Okay. Let's have a think. Back to the diagram. So, okay. Obviously, if P... Right, this is interesting, and this is to do with the direction the friction is going in. Imagine P is just holding on here in terms of if P was any weaker, the ladder would fall kind of that way. In that case, the friction would be acting this way because both P and F are trying to force that, are trying to stop the ladder from slipping. So let's consider that for now, and then we'll think of something else. If that was the case, then doing left equals right would get us everything taking it to the left is just going to be this RB, and everything taking it to the right is going to be F and P. So we're going to get RB equals F plus P. We know what RB is, it's 3W, we worked that out last time. F, can we work out F? Well, I think we can, because F is going to be less than or equal to mu r, isn't it? So instead of using this equality here, what I'm going to do is I'm going to get F on its own. So what I'm going to do is I'm going to take P from both sides. I'm going to get 3W and then minus P equals F, okay? Now, is there anything that says, it's in limiting equilibrium or anything like that? I don't believe it is. So, when it says it's in limiting equilibrium, then we can say F is equal to mu r, but it doesn't say that here, meaning that F is going to be less than or equal to mu r. So this F is going to be less than or equal to mu r, okay? Meaning that 3W minus P is going to be less than or equal to mu r. Okay, now this R is the reaction force at A, because the friction is at A, okay? Meaning that we need to work this out. But we can work that out relatively easily, because if I do up equals down on this, let's just do it quickly here in blue. So up equals down, everything taking it up is just RA. Everything taking it down is W plus 7W. So RA is going to be 8W. Okay, this is nice. Meaning that mu is equal to 1/4, I believe. RA is equal to 8W. So what does this tell me? This tells me that 3W minus P, and then this is equal to 2W. So I get 3W minus P is less than or equal to 2W. So adding P to both sides, I'm taking 2W from both sides. I get 3W minus 2W is less than or equal to P, meaning that P, in this case, has to be greater than W. Cool. Now, I don't think that's enough, because this is saying that P can be however big it wants, okay? So let's imagine, right, that this builder's assistant is hench, right? He's got some force, and he's pushing it so hard, right? At the start, what he's trying to do is he's just trying to stop it from slipping, right? So he's trying to stop the ladder from going this way by applying a force this way. And in that case, you know, the friction is still going this way. But now let's imagine that he's so hench that he actually almost makes the ladder go this way, right? If he's actually pushing the ladder this way, or if it's on the point of slipping that way, then the friction is then actually going to be going in the other direction. So in that case, P would still be going here, it would probably be quite big, but then friction would be going the other way, because then it's like, whoa, steady on actually. I thought I was trying to stop this guy slipping, and now you're so hench that like it's going to go the other way. So in this case, I would actually get friction going this way. This would be in the case that P is large, right? So this is like that top end of P. In this case, what would the left equals right be? It would be F plus RB is equal to P, right? F plus RB is equal to P. This is when P is big, right? So F plus RB has to be equal to P. Okay, so then let's have a think. RB, that's not changed, has it? So we know that RB is still at 3W. The friction, that's not changed because that's still just going to be mu R. So that's going to be the 2W. So now, I still need an inequality. So instead of putting this here, I'm going to get F on its own again because I think that's the way to get it not confusing. So F is equal to P minus RB in this case. And now we know that F must be less than or equal to mu R. Okay, so if P minus RB is less than or equal to mu R, then mu R we know is 2W here. So that's the mu R. So we get this. Okay, fantastic. So now, subbing in the RB, which we know is 3W, I must get P minus 3W is less than or equal to 2W. Adding 3W to both sides, I'm going to get what? I'm going to get P is less than or equal to 5W. So this works. I've got a lower end of P, which is like, you need to put this much force in so the ladder doesn't slide down. But then I've also got an upper end of P because it's like, if you put too much force in, the ladder's going to slide the other way, right? So in other words, P must be greater than or equal to W and less than or equal to 5W. And I believe that that is the answer there. That was tough. That was a very hard question. I had to think there. Often in practice, the builder's assistant will simply stand on the bottom of the ladder. Explain how this helps to stop the ladder from slipping. Okay, so let's imagine that he's standing on the bottom of the ladder. So now, I suppose this is a bit interesting, isn't it? Because you're obviously trying to stop the ladder slipping this way, but you're now not even going to be applying a horizontal force, are you? You're now going to be applying, instead of applying this P here, you're going to be stood on top of here. So if you're stood here and you've kind of, you know, got whatever your weight is going down, now again, friction would, as normal, be acting in this direction again. I've got this friction here, haven't I? So, well, the only thing stopping it is the friction here. But friction's going to be more. Why is friction going to be more? Because friction is equal to mu R, isn't it? But imagine, you know, this reaction force here, which is kind of a function of, you know, the weight that's on it and the mu. Well, the mu's not changed, has it? But now I've got all of this guy's weight stood on the ladder. The reaction force is going to be much higher now, isn't it? Much higher. You know, if I was to kind of do up equals down here, I would have the extra weight of the other guy, whatever his weight is, making the reaction force have to be a lot higher to balance it out. So what's going to happen in this case is that standing on the ladder, can't type, will greatly increase the reaction force at A, which will therefore increase the frictional force at A. you know, if you really kind of, if you got a bit of time in the exam and you want to kind of scramble for marks, you could maybe even explain this a bit more using a bit of maths, because you would say, okay, well, up equals down now. I would have the reaction force at A is equal to the W plus the 7W that we had, but plus the weight of the other assistant. So the reaction force at A is now equal to the 8W from before, plus, let's call this W2, where W2 is the weight of the other assistant. So it's obviously going to be, you know, much greater than the old reaction force. Therefore, the friction, the new friction, is going to be much greater than the old friction, which is going to help to stop the guy from slipping. Last question, we've almost survived. Let's have it. A boy throws a stone with speed u from a point O at the top of a vertical cliff. Point O is 18 meters above sea level. Stone is thrown at an angle of alpha above the horizontal. Tan alpha is 3/4. They've done it again. Stone hits the zeta point S, which is at a horizontal distance of 36 from the foot of the cliff, as shown in figure 2. The stone is modelled as a particle moving freely under gravity with g equals 10. Okay. Find the value of u. Right, so projectiles is all about the suvats, okay? It's all about your horizontal suvats and your vertical suvats. So let's try and set them up. So horizontally, what's kicking off? And then vertically, what's kicking off? Because they're independent. Let me just see like where we want to do this suvat, okay? So I think it's probably going to be the whole motion. And the reason why is because we have information to do with that. We know that it hits the sea 36 meters away. And we also know that vertical distance. So I think if we do suvat on the whole thing, we're going to be good here. So u horizontally is going to be the horizontal component of this u. So if we look at it, we have u is going up here at alpha, meaning that the horizontal component is going to be u cos alpha, and the vertical component is going to be u sine alpha. Now, we know what cos alpha and sine alpha are because of our triangle with the tan. So I'll do that quickly for you. We're told that tan alpha, as we always are, right? You should be very used to this by now, is equal to 3/4, so opposite over adjacent. Pythag gets that as 5, meaning that cos alpha, which is adjacent over hypotenuse, right? Ka. So cos alpha, let's do that here, it's going to equal 4/5. And sine alpha, which is equal to the opposite over hypotenuse, is going to equal 3/5. Okay, so the u for the horizontal is going to be u cos alpha, or 4/5 u. The v, I don't know it. The a horizontally is 0. Because there is gravity acting on this, but gravity acts completely vertically downwards. So there's actually no horizontal acceleration or deceleration here. In real life, there'd be air resistance and stuff like that, so it would have an effect, but we're assuming no air resistance here. So A is going to be 0. T, I don't think we know that either. Do we know S? Yeah, I think we do know S, because S is going to be the horizontal displacement. We're told that it hits the sea at point S, which is at a horizontal distance of 36. So that's going to be 36 here. Cool. And then V, I don't know. T, we don't know that either. What we do know is that the T is going to be the same as the T here, though, isn't it? So that is the one thing shared between the two. So let's have a look. S, we know that between the origin, the top of this cliff, and the sea, it has displaced a negative 18 meters. So S is going to be minus 18 here. U is going to be the vertical component of this initial, which is going to be u sine alpha, which is going to be 3/5 u. V, don't know it. Acceleration is going to be due to gravity. Acceleration is going down, and we're taking positive as upwards, so the acceleration is going to be negative. It's going to be minus g, which in this case is going to be minus 10. Okay, we've got our two Suvats. What do we do with him? We want u. It's a bit tough, isn't it? Because there's actually two unknowns. I can't just get u from this, because there's one unknown, two unknowns. And then again, two unknowns. So what we're thinking? Two unknowns, two places I can get equations. You guessed it. Simultaneous equations. Do a Suvat on this, get a relationship between u and t. Do a Suvat on this, get a relationship between u and t. Solve them together. So s equals ut plus a half at squared is going to be the formula that we're after here. So doing that horizontally, I'm going to get the following. Let's go blue. So I'm going to get s, which is 36. So horizontally, s, which is 36, is equal to ut, so 4 over 5u times t, plus a half at squared. But look, a is 0, so that whole term's going to go, isn't it? So that's what we have horizontally. Vertically, we have s, which is minus 18, equals ut, so 3 over 5 ut, plus a half at squared. So plus a half a, which is minus 10, times t squared. So here we have two simultaneous equations. Let's see what we can do with this one first of all. Because I want u, I feel like I'm going to want to... What's going to be easier here? Why don't we... So I'm going to have kind of quadratics in t here. If I eliminate t, I'd get a quadratic in u. So it's either, I suppose. We can either try and eliminate the t's, get a quadratic in u, or eliminate the u's, get a quadratic in t. Let's have a look at... So part B wants the speed. I feel like I want the t values here. So I might not, but I'm gonna get them anyway. It doesn't matter. Let's do 36 divided by 4 over 5 here. What am I going to get? 36 divided by 4/5 is going to get me 45. So 45 is equal to ut. Okay, that means that let's get u on its own here. So that u is going to equal 45 divided by t. Let's see what we can do to clean this up before I start subbing anything else in. I'm going to get minus 18 is equal to 3 over 5 ut. Minus 10 times a half is going to be minus 5t squared. Okay, let's sub it in and see what we get. Okay, so minus 18 is going to be 3 over 5 times by 45 over t multiplied by t minus 5t squared, which is going to equal, well, 45 over 5 is 9. Yeah, times that by 3, I'm going to get 27. And then I get a divided by t and a multiplied by t, there you go. So I get 27. And then minus 5t squared here. I've got a quadratic in t, haven't I? So I'm going to get I'm going to add 5t squared to both sides. And then I'm going to add 18 to both sides to get 27 plus 18. So I'm going to get 5t squared is equal, well, 27 add 10 is 37. Add another 8, I'm going to get 45. What has gone on there? I'm going to get 45. Divide both sides by 5 to get t squared equals 9. And square root both sides. So I'm going to get t is plus minus 3. Now t represents time, so time can't be negative. So t is just going to equal 3 in this case. Okay, so if t equals 3, I can now sub that in to get u. So u is going to equal 45 divided by 3, which is going to be 50. Whew, fantastic. Part B, I want the speed of the stone when it is 10.8 meters above sea level, giving your answer to 2 sig fig. Okay, 10.8 meters above sea level. So where is that? Remember, I start 18 meters above sea level. So 10.8 meters above sea level. If this is 10.8, what would my actual displacement be? Well, my displacement vertically would be everything down here, which is going to be the difference between 18 and 10.8. So if I was to do 18 minus 10.8 in my calculator, I'm going to get 7.2. So actually, I've got this distance here is 7.2 meters. That's going to be important, because if I was to set up a SUVAP vertically, I'm probably going to do one horizontally as well. Vertically, I would get the following. You know what? Let's put this here. Okay, so vertically, my displacement is going to be minus 7.2 because it's downwards, okay? U is the same, it's the initial, which we know to be U sine alpha. So 15 times sine alpha, which we got as 3/5. V, we don't know that yet, but I think that's what we want because we're asked for speed. A, again, it's minus G, so minus 10. So I think I'm good in this case. I don't know time, but I don't need it. So, acceleration, S, U, and V. I believe I can use V squared equals U squared plus 2AS. And I want V squared here, don't I? So U squared, well, what is U? 15 times 3/5. The 5s are going to cancel. 15 over 5 is 3. Times that by this 3, I get 9. So V squared is going to be 9 squared plus 2 times minus 10 times minus 7.2. Stick it in your calculator. 9 squared plus 2 times minus 10 times 7.2 gets me 200 times minus 7.2 gets me 225, which is actually fantastic because that's 15 squared in it. So V is going to equal, well, it's going to be plus minus square root of 225, which is 15. Which one's relevant here? Well, think about the direction it's moving in, right? You know, it goes up and then it's going down at this point, isn't it? So my vertical velocity is actually negative because I'm going down. So V is going to equal minus 15 here. Okay, that's not the final answer though, is it? Because I want the speed of the stone. Speed is made up of both your horizontal and your vertical velocity. Now, we know the vertical at this point is going to be minus 15, so this length is 15 downwards. Horizontal is never changing because, as we said, there is no horizontal acceleration. So the horizontal velocity at any point is just the same as the initial horizontal velocity, which we know to be U cos alpha. We know that U is 15, and we know that cos alpha is 4/5. 15 multiplied by 4/5, which is equal, well, that cancels to make 3. 3 times 4 gets me 12. So I now just need to do Pythagoras here. I've got 12 and 15. So the speed is going to be the square root of 12 squared plus 15 squared, which I think it's going to be something nice. Not really, no. It's going to be 3 root 41. And now we're told to give our answers to 2 sig fig, so I'm going to press SD, which is going to get me, well, to 2 sig fig, 19 meters per second. Whew! So just 2 improvements that could be made to the model. Okay, quick one. The first classic, include air resistance, right? That's going to change everything. It's going to actually, you know, probably give us a deceleration horizontally instead of A being 0. It's as important. So we're going to want to include air resistance. And then there's a few things here. I mean, the first thing is they've said use G as 10. That's not that accurate, is it? So we could use a more accurate value of G. Well, that's 2 right there, but let's see if we can think of any others. Again, wind, right? It's not quite the same as air, because you could just have like a sudden gust of it. So, you know, you can definitely account for wind. Think about it. This ain't going to be the same in some proper windy beach on the edge of Portugal. than if it was just in some really dead, no-wind place. It's obviously going to be different, you know, irrespective of air resistance. So we can account for wind. And then the other one is that we modelled this ball as stone as a particle. In reality, it's going to have a shape, right? It's going to flip about, maybe. It's going to spin. So basically account for the shape, you know, the dimensions of the stone. And I think that's more than enough ways to improve the model to be getting on with. Whew. We're done. It was grim. I think I survived it in the end, though. I've got some more past papers and stuff lined up and some other videos. But not just papers. I will provide you with my maths nerd brain, right? If there's anything, any topics or little things that you want to see covered in a video, let me know in the comments. I want to share the knowledge of a maths nerd. So, apart from that, I will see you next time.